We present visual force-torque sensing, a method of estimating the forces and torques applied to a soft robotic gripper using single frames from a gripper-mounted camera. We trained a convolutional neural network to minimize the error between measurements from a force-torque sensor and the estimated forces and torques from our network given a single image. Notice how both of our selected grippers visibly deform due to external forces and torques. This visible deflection is what makes it possible to estimate forces and torques given only visual input. We trained our network in a suite of environments using a Stretch RE1 mobile manipulator from Hello Robot. Our training set included approximately 2 hours of footage in various lab and office environments. After training a convolutional neural network on this data, we test our method on a held-out household environment with unseen objects. See the performance of our network on the test set. The ground truth is indicated by darkly shaded arrows, and the estimations by our network are indicated by lightly shaded arrows. We also train a separate network with the manually operated pneumatic gripper in various environments, and test on a held-out office environment. We evaluate both networks by calculating the root mean squared error on the test sets. Our method performs well when compared to a motor current baseline and a mean guesser. Our method generally captures strong relationships between the input images and the corresponding forces and torques. Notice, however, that our method struggles to visually estimate forces in the depth direction. Despite these limitations, our method is capable of providing useful sensory output for a variety of applications. We prove the utility of our method with 3 autonomous robotic tasks. In the blanket grasping and pulling tasks, the gripper is first lowered onto the edge of a blanket until an estimated vertical force threshold of 3 newtons is exceeded. The blanket is then grasped and lifted. The robot then drives toward the top of the bed. Once the blanket is taut and our network detects a horizontal force above 2.5 Newton threshold, the gripper is lowered and released to place the blanket onto the mannequin. We successfully complete both subtasks in 10 out of 10 trials. In the third task, bed bathing, the gripper is lowered onto a mannequin's arm or leg until a force magnitude threshold of 6 newtons is reached. The plane tangent to the surface is then assumed to be normal to the estimated force, and the gripper moves along this tangent plane and continuously updates its estimate of this plane. Simultaneously, the force normal to the surface is regulated in order to maintain contact with the surface without exceeding a maximum force of 10 newtons. We successfully cleaned an average of 87% of dry erase marker off of the mannequin's arm and leg after 10 trials. Our work presents a promising direction for visual sensing. We intend our method to be a viable, cheaper alternative to traditional force-torque sensors, and we hope this work leads to more accessible robotics research around the world.